my talk today is going to be about the Groq runtime. And this is the same runtime that is used by Groq Flow under the hood, as well as is available as a standalone tool as part of our SDK to just run your models, separately from Groq Flow. Runtime is a bit of an overloaded term in the industry, I think. So in a few slides, I'll kind of specify what I mean when I say runtime. But before getting to that, something I want to note is that this presentation is going to be for our currently publicly available runtime as part of our SDK. With the release of LLMs, we put a lot of time and effort into changing parts of our runtime to allow for performant LLM running on our hardware. These changes are not going to be are not yet public, and so I'm not going to be talking about them quite yet. But assuming everything keeps going well, in future Groq SDK releases, hopefully I can talk about these LLM specific runtime changes, at which point Hatice or anyone else can bring me back and we can talk about those changes. So actually, one last thing before we begin, I want to make this as interactive as possible. So if you have a question, I can't see the chat. I can't easily see the chat. So if you have a question, just unmute yourself, or Hatice, if you see any messages in the chat, feel free to just interrupt me and I'll try and answer them. Sound good, folks? I don't expect an answer. Let's begin. Cool. So the first thing in this talk I'll discuss is the kind of runtime and hardware software architecture as it relates to Groq Flow, as well as how it relates to just how you'd run any model on Groq hardware, regardless of Groq Flow or not. And hopefully a lot of you have seen the Groq Flow presentation, I think yesterday, by Sanjeev. So that'll kind of tie into what Groq Flow is again. And second, I'm going to talk about the ways you would interact with the Groq runtime as a developer. And third and finally, if we have time, I'll do a deeper dive on running inferences on a GroqChip at kind of more of a byte transfer level. So what is happening really like at the byte level of transferring data from the host CPU to the GroqChip and vice versa. I hope that sounds good, and we'll keep going. Anyway, like I mentioned, I want to define what a runtime is. So before going further in my talk, I just thought it would be useful to define what I'm going to talk about a runtime to be. So the runtime is a higher level piece of software that's running on the host CPU inside of a Groq node. And this runtime software communicates with whatever your Groq hardware is using a VFIO based driver that we've written. And the Groq driver facilitates this communication between the CPU and the GroqChip over PCIe. The Groq runtime deals with parsing information inside of our IOP files. Can you guys see my mouse, by the way? You can. Okay, great. So yeah, it deals with IOP files, which is our programming file for Groq hardware, and kind of defines your model weights and what your model expects for inputs and outputs. And for larger models, this is still a new feature that's coming out. The Groq runtime facilitates model parallelism, where you can shard up a large model across many, many different Groq chips, excuse me, to run that model in a distributed kind of fashion. So this picture is very busy. Don't stress about what's on it right now. We're going to come back to this picture again and walk through the important system components step by step. Anyways, whoops. Now that we have runtime a little bit more defined, I'll tie it into something you've seen before and something you're more familiar with, which is Groq Flow. So you should have seen this slide in Philip's presentation and a version of the slide yesterday during Sanjeev's presentation. So as you can see, this is the Groq Flow kind of tool flow. And so, like I mentioned, the block I'm going to describe in Groq Flow is the Groq runtime, which is that block right here. So when you're using Groq Flow as a developer, you aren't directly using the runtime, but under the hood, Groq Flow is making calls to and from our runtime component. This diagram is a little misleading as it combines many, many different system components into the runtime block. So I'm going to peel the onion back, so to speak, a layer or two, and show you what that Groq runtime block is really made of. So like I said, I'm going to return back to this diagram. And that runtime block from the previous slide is really the expansion of kind of this entire portion. I'm going to change this just a little bit more to really kind of focus in on what I want to talk about. So these blocks that I just highlighted in orange are primarily what I consider to be the runtime and its various components. So we'll now step through these blocks one at a time, and I'll kind of give you a high level overview of what each is doing. So revisiting the runtime block one final time, like I said, just think of the runtime as a higher level abstraction interface to interacting with Groq hardware. So it's kind of like a top level API for how you interact with our Groq hardware, be that a single chip, an entire node of chips, a rack, or multiple racks. The Groq runtime has code for parsing our IOP file formats, initializing the chip, allocating input and output host buffers in the host CPU memory, and ultimately kicking off an inference, which we often term as invoking a program. So coming back to this, I'll just put a little green check mark on the Groq runtime to denote that we've talked about it and you have a high level understanding of what's going on. Next, I want to talk about how we bridge the gap between compile time and runtime, which is really with the IOP file. So the IOP format, or the input-output package file format, is our representation of an executable for the GroqChip. This would be an ELF file, a .elf, or an a.out file on a traditional CPU. So described in other terms, an IOP file is our compiled and scheduled program that is your compiled and scheduled model that can be executed on our hardware. And the IOP contains all your model weights and the kinds of inputs your model is expecting, as well as the output your model will give you once your inference is completed. And just to kind of show how we bridge compile time and runtime, it's that IOP file. So this diagram here at the bottom is just my little way of showing how we bridge that gap. Putting a little green check mark on IOP and just rolling along, I want to move on to the Groq driver. This is a small piece of software, low-level piece of software that's running on the host CPU. And you can think of the Groq driver as the interface to the GroqChip via a PCIe interface. The driver is involved with some of the DMA transfers to and from the GroqChip from the host CPU, as well as handling certain CSR reads and writes. Moving back to this slide, we'll check off the Groq driver. And something I just want to mention, in this diagram, I isolate the Groq runtime and Groq driver, but that's a bit of an artificial distinction. In the code base, the runtime and drivers codes are fairly intertwined. So they're kind of like the same piece of code, but for the sake of this presentation, I wanted to separate them. And I just want you to think of the driver as the part of the code that deals with shuffling data from the host CPU to the GroqChip and back and forth, dealing with that kind of communication. Whereas the runtime is meant to be this higher level abstraction that you as a developer or programmer would more interact with. So with that said, let's move on to the next part of the system I want to talk about, which is our Groq hardware. And so Groq hardware comes in a variety of flavors, we'll say. In the ALCF pool, I don't know if pool is the right term, you have access to a Groq rack, which we define as 9 Groq nodes. And one Groq node contains 8 Groq cards, and each Groq card contains a Groq chip. So if you kind of do the math, 9 Groq nodes times 8 cards per node, you have a total of 72 Groq chips in the Groq rack in the ALCF pool. Yeah. So just kind of saying that for this talk, I'm just going to really focus or pretend like we're programming a single card just to make it a little simpler. But similar principles for programming a single card apply to programming, multiple cards for larger models that you might want to shard across multiple chips. And then on the right here, I just have a few pictures of what some of our hardware looks like, if you were curious. Okay, checking off the Groq hardware box. The last 2 boxes I'm going to talk about are the host CPU and the PCIe interface. But I'm not going to really dive very deep into this, as I don't feel like it's super relevant to the runtime. I can't answer any questions that you guys have about this, but we're running in our Groq node, we have a host x86 CPU, and we communicate to the GroqChip. The main data path we communicate is over PCIe Gen 4. So that covers every single system component block of what I consider to be the runtime. And at this point, assuming I didn't go too fast, you should have an okay idea of the purpose of each component in the overall kind of running an inference on Groq hardware. I'm going to switch sections kind of soon, so I'm just going to take a pause. Are there any questions in the chat, or does anyone have any questions or want me to dive deeper onto anything before I go on? I will take silence as no, so I'll keep going. So like I said, I'm going to now switch gears a little and slightly up-level the conversation. Instead of talking about the various components that make up the runtime, most of you who are ML researchers or ML developers will interact with Groq hardware just leveraging the abstraction of the runtime. So kind of that top-level runtime block. So I just wanted to talk about the various types of runtimes we have that you would interact with. And something else I want to clarify is that there's kind of more than one Groq runtime, which is a little strange. They all leverage more or less the same code, but depending on what your end goal is and if you're using Groqflow or not, you're using different runtimes. So in the next few slides, let's kind of just cover what some of the different runtimes that you as a developer might consider using and would use in your programming of Groq hardware. So first, I'll again kind of highlight the blocks that are the different runtimes we have available to you. The first major distinction between all these three blocks, these runtimes that we have, is whether they are Python or C++ based. So both the C++ and Python versions of the runtime can offer similar performance. So don't let the fact that one is in Python turn you away from getting high performance. But the driver, the C++ driver, this blocks down here, is natively written in C++. So writing a C++ API to communicate through the driver is fairly straightforward. But we also support Python, and we have a Python FFI, a foreign function interface kind of veneer for how you can use Python in call some of the lower level runtime API calls that you might want. Anyway, I'm getting ahead of myself. Assuming you choose a language, C++ or Python, you have various options. One of the biggest distinctions I want to make, aside from language, is just if you're focused on ease of use or if you want to get high performance. If your goal is ease of use and you just want to get your model up and running on Groq hardware to see it's working and do some slight model tuning, then you would probably use the Python-based TSB runner runtime. The Python-based TSB runner is a great runtime to use in your application for a quick proof of concept. And it really abstracts away a lot of the lower level kind of hardware details, allowing you to just have your model, compile it in the Groq compiler, and get it running on Groq hardware pretty quickly. And for example, GroqFlow uses the TSB runner runtime under the hood, so that when you compile a model in GroqFlow, you're running it using this TSB runner runtime, which is very easy to use. We are sacrificing a bit of performance for ease of use with this. So if performance is something you're after, then you'll probably need to use one of the runtimes that are highlighted on this next slide, which are just the base Python or C++ runtime APIs. Both of these lower level APIs give you more control over your model's performance on our hardware and really allows you to extract the most performance while running on our hardware. The trade-off is that you do need to know a little bit more about how the Groq programming model and hardware details, but that isn't information that's difficult to learn, and we have a lot of documentation explaining how that works, so that you can get the maximum performance while running on your Groq hardware. So that'll finish out how you interact with the with Groq hardware, or with the Groq runtime, excuse me, as a developer. Before I switch gears one last time, are there any questions? No? Awesome. Okay, so with that high-level overview I gave of runtimes and explaining all the different kind of system components that build up a runtime, I wanted to kind of do a little deep dive through what's actually going on under the hood when you're trying to run an inference on a Groq chip. So this talk again will abstract away some details. So if there are any questions you have about what's going on at kind of the byte level, feel free to ask. So for this example, let's say that we want to run some image classification model on our Groq chip. Let's say ResNet 50, just to make this a more concrete example. So we'll start out with an input buffer and an output buffer in our host CPU memory. And you can see this rainbow kind of array, these rainbow vectors, that let's assume that to be your input cat image that you want to run through ResNet 50 and classify it. And then the output buffer is empty for now, but through running an inference, we'll fill this buffer with an output. So moving on kind of quickly, the first thing we need to do is transfer the input buffer data to the Groq chip. So there's this is the Groq chip over here. It's unfortunately not labeled, but host CPU and Groq chip. So how do we move data from the host CPU to the Groq chip? We do this with a DMA transfer between the host CPU and the Groq chip using this thing called a DMA descriptor. And for brevity's sake, I won't go into DMA descriptors very much. Just think of it like a linked list of addresses of where the Groq chip needs to kind of read memory from. So the first step to kick off an inference is that the Groq driver will write a DMA descriptor to the PCIe block inside or on the Groq chip. And when the Groq chip's PCIe block detects that a DMA, that a descriptor has been written to it, it'll kick off a DMA transfer of this information into the Groq chip. So the DMA master in the Groq chip will read or pull down information from the host CPU, and will start filling a FIFO in the Groq chip. As it reads information, it'll fill the FIFO kind of one memory location at a time. As this data is copied over into the FIFO, the received FIFO, data is also simultaneously popped out of the FIFO into SRAM locations on the Groq chip. So this slide transition is just to show that as we were reading information, we popped some data into predefined SRAM locations on the Groq chip. And these SRAM locations, like where your kind of model weights go or your inputs go, are defined in your IOP file, and that's parsed by the runtime. And there's some code on the Groq chip that can read the IOP file and program certain SRAM locations with the correct weights or input data. So we read all of our data from the host CPU and we push it all to chip's SRAM. And at this point, with all the input data copied over, we can now run our inference. So this next slide, we've run our inference at this point, and you can see I've denoted this with the blocks that were white before here have now been filled in with this kind of gray output, which is to denote our output data. So the next step is to take our output data and get it back to our host CPU so that we can analyze our results. And the way you do that is kind of the inverse of what we did to get data onto the Groq chip. So first, some code on the Groq chip will run, and it'll copy the output data from SRAM into an output FIFO in the PCIe block. And then to extract the output data from the chip, the driver the driver writes a DMA descriptor of the output buffer in the host memory to the Groq chip. This step actually happens immediately when you run an inference. So an input DMA descriptor and an output DMA descriptor get written to the Groq chip immediately when you run it. But just for the sake of this kind of flow, I'm showing it as taking two different steps. Anyway, and like the Groq chip knows where to write its output information to. So it'll kind of write that information back out into the host CPU's output buffer. And at this point, you can read that data in your CPU program, and the image classification is done. If it's a cat or not, you'll probably know at this point. So that was kind of a slightly deeper dive at the byte level of what might be going on.